All right, so now is the time for the last talk. We call this talk good practices to use geometric methods, and I would say that right now you might be kind of experts on the reasons why geometry is necessary. The motivation of this talk, which basically comes from a paper that we published in ICRA this year, is the fact that we observe that out there many folks are basically misusing some of the concepts of Riemannian manifolds in downstream tasks. And our idea was to raise awareness that these works have been actually reproduced and that we are actually reproducing flawed approaches. So to get started, I will just do a quick recap on the tangent space. So for you, this could be very repetitive, so I will try to go very quickly. So as we said before, many times, we're assuming that our manifold is smooth and that therefore, locally, we can define tangent vectors, which are or corresponds to the derivatives of a curve for a specific point on the manifold. And based on that, we can get the notion of the tangent space. That, because of the assumptions that we have so far, is basically Euclidean space. The collection of all these tangent spaces form what is known as the tangent bundle. And therefore, the key idea here for many of the applications that we see out there is the fact that all the Euclidean operations are possible in the tangent space. So with this in mind, right, the question is, okay, so we have tangent spaces that are actually Euclidean. Can we just, in the sense of optimization or learning problems, project everything to a single tangent space and use any out-of-the-box algorithm out there? And you might already know the answer for that, and it's that we shouldn't, or we must not. And to motivate the why not, this is not a good solution, I will walk you through a very simple example, which is density estimation. So here we have a very simple manifold. Its constant curvature, positive is the sphere, and we have some data that we collected. This can be for any kind of application, but let's say it's a very simple data distribution. Denoted as black dots here. And what we're gonna do first is to do density estimation using a simple Gaussian mission model. So one of the simplest density estimation models that we can use out there. And what we're gonna do is that we're gonna define a tangent space, in this case on the north pole of the sphere, and we're gonna project all our data to this tangent space using the logarithmic map, and then we train out-of-the-box Gaussian mission model, and we estimate the density like that. If we do that, and we project back the density to the manifold, this is what we get. So the first problem that we can observe here is the fact that, okay, probably here in the projection is not super obvious, but we don't have zero density in the center of the manifold, which we are supposed to have. But probably also what you can see is that we have very high densities where actually we are not supposed to have it. And this actually comes from the fact that we are projecting everything to a single tangent space and learning a Gaussian mission model on it. You might think like, okay, maybe I just choose wrongly the tangent space. I should maybe use one that is more meaningful for the data at hand. So, okay, I could agree with that. So let's use another tangent space where the base point corresponds to the Freshet mean of the data. So that could be like a good estimate, right? And we do the same. We project the data to tangent space, and now we learn our Gaussian mission model, and we project it back. A little bit better in terms of the log density that we are computing, and also on the fitting that we have here. However, for example, here at the bottom left of the density, we we observed that actually we have zero density, which is not true. So actually, a better thing to do is to use multiple tangent spaces, in this case, per cluster in our Gaussian model, where the base point is defined as the Fresnel mean for each of the clusters that we have. And then we learn a Riemann and Gaussian model. If we do that, this is basically the best result we have. This is a very simple example, low dimensional data that are actually well behaved. And we are observing that if we use a single tangent space, things can get really inaccurate. So with this in mind, basically what I want to talk about right now is something that we called the single tangent space fallacy. So something that we have observed out there in many works that basically build on some misconceptions regarding the use of Riemann geometry, and specifically the use of the tangent space when it comes to downstream tasks. So the first fallacy, it comes to the fact that the exponential map in Riemann geometry is just a local diffeomorphism, right? So what that means is that in this example, if I have two vectors on the tangent space, ut and u3, and I compute the exponential map, what could happen is that I boil down to the same point of the manifold. So therefore, it's not a diffeomorphic mapping anymore, it's not bijective. And what basically that means is that the exponential map is only a diffeomorphism in the unit in the injective radius, and this injective radius actually depends on the curvature of the manifold that we're working with. The second fallacy is that the exponential map is not an isometry, so therefore it doesn't preserve distances. What this means is that if we actually want to use distances, for example, to define a cost function, and we are using distances that are measured using the log map, this doesn't correspond and is not measuring the same thing as if we're using the geodesic distance on the manifold. So just to illustrate this, basically here we are going back to the example that we had before on the sphere. And what I want to show here on the right is that when we project the data on this single tangent space at the pole, you can see that the data are highly distorted, right? So this already tells us that this mapping is actually not preserving the distances that we observe in the original manifold. The third fallacy, before that, here what we want to show is the effect that using this single tangent space has in other kind of settings. So what we wanted to show is, okay, does this single tangent space approach might still kind of work for higher dimensions or for other kind of densities? So what we did here was to basically run the same three approaches that I explained before. So basically Euclidean GMM. So this one doesn't consider the geometry at all. So let's disregard the geometry. The other one is like, okay, let's use the tangent space and train a GMM there. And the third approach is the Riemann GMM that we observe here on the left. What we show here in the table is two cases. So the first one is when we use a mixture of Riemann and Gaussian distributions. So what we did was to define by hand a set of mixture of Riemann and Gaussian distributions that are defined on the sphere manifold. We created synthetic density of this mixture, and then we sample 100 points, and we fit the Gaussian model on top of that. We did it for different dimensions. So here we have dimension number 2, 3, 7, and 10. The idea was to show actually like how inaccurate actually the other approaches might become when we increase the dimensionality for this example. And as you can see here at the bottom, we are reporting the log likelihood for a new samples that we have for the density. And as you can see here, the difference in the log likelihood actually are dramatically different as we increase the dimensionality of the manifold. So that's already telling us that if we start working on higher dimensional manifolds, this single tangent space approximation is pretty bad. Something similar happens when we use a mixture of von Mises Fisher distribution, which are intrinsic distributions that belong to the sphere. And we have a similar behavior. We run a very similar example, but now on the symmetric positive definite manifold. Because our idea is that sometimes what we have observed in some works is that as the geometry of the sphere is kind of well behaved, and it provides a constant curvature, maybe sometimes people may think that this single tangent space might work out. If we change the manifold, what we did was exactly the same thing. So we have the three same methods, so the Euclidean GMM, the tangent space GMM, and the Riemann GMM, and we trained two different kind of models. So one on a mixture of Riemann and Gaussian distributions on the SPD manifold. We did exactly the same process. So we created this distribution by hand, then we sampled 100 points out of it, we feed the density, and then we evaluated the log likelihood. We did it for the SPD manifold in 2 dimensions and 3 dimensions. As you can see here, basically the differences are also quite big, just for 3 dimensions. We did a similar test, but using a mixture of inverse Fisher distributions, which are basically kind of intrinsic distributions for the set of symmetric positive definite matrices, and we have a very similar result. So all in all, the Riemann and Gaussian Michaux model is basically the one that provides the best log likelihood for all the dimensionalities and for all the tests that we run. Now we're going to move to the third fallacy. So this might look very simple and very obvious for many of us that play with dynamical systems on Riemann manifolds, but the idea here or the concept here is pretty simple. So velocities on Riemann manifolds, of course, are attached to the positions in which these velocities belong to, right? It's a very simple notion. However, there are some works out there where this dynamics is kind of projected to a single tangent space, and then they fit or they learn these first order dynamics. So here we are only talking about first order dynamics, then the problem gets even nastier. We're talking about second order dynamics. And what I want to show here is kind of a similar toy example that we run. So here we want to compare 3 different approaches. So the first one is that we want to learn a very simple first order dynamical system on the sphere using some training data. So on the top, we have this kind of S-like shape. At the bottom, we have this kind of W-like shape. In white, we have kind of the demonstration, so to speak, so the training data for our model. For now, we don't care which kind of model we are using, but for those that are interested, basically, it's a Riemannian normalizing flow. So it's a kind of more sophisticated density estimation algorithm. And the idea is to learn this first order dynamics on the manifold. First approach is this projected Euclidean dynamical system, which basically learns a normalizing flow only on the Euclidean space, so I disregard the geometry, and then I project the solution back to the manifold. For example, in this case of the sphere, I just normalize the positions. The second approach is using the tangent space dynamical system, and this, as you can see here, I'm not showing the vector field, because just the idea of projecting your dynamics to a single tangent space is just breaking the whole theory. So actually, we are not able to recover from the vector field that we learned in tangent space a vector field on the manifold. There's no way to do that. And this is the reason why, for example, here, this is the tangent space projection. So here, this is the normalizing flow on the tangent space that we learned. And you can see that this S shape is severely distorted. This vector field that we learned here, whatever we learned, because actually it's quite flawed, we cannot project it back to the manifold. Because the velocities that we observe here in the tangent space actually don't have any physical meaning if projected to the manifold. And then what we did was to learn a Riemannian normalizing flow. So one normalizing flow that actually accounts for the geometry in a natural way. And as you can see here, the vector field looks actually pretty decent. When we try to roll out trajectories following the dynamics that we learn, they follow the pattern of the training data. And with these kind of approaches, we are able, for example, to learn dynamical systems where we can endow that model with some stability guarantees on the manifold. For example, the notion of Lyapunov stability or the kind of stability notions. To give you some quantitative experiment data. So here we are showing what is called the dynamic time warping distance between the trajectories that we use for the training, so the demonstrations, let's call it like that, and the ones that we actually obtain from the learned dynamics. So at the bottom, you see the Riemannian approach, and is the one that actually shows the best performance in terms of the dynamic time warping distance. So basically, it's the one that provides the closest fit into the demonstration. We can also compute something that is called the success rate. So if I roll out my dynamics from different points on the manifold, I want to measure how many trajectories reach the final point of the dynamics, so to speak, the equilibrium of it. And the Riemannian case is the only one that actually reaches almost 100% the equilibrium point of the dynamical system that we learned. All right, so now let's move to the fourth fallacy. So here, I guess that you should be already convinced that Riemannian manifolds and Lie groups are actually not the same. We need to endow them. So basically, they represent different entities. And the idea of highlighting or emphasizing this fallacy is because of the following reason. So what happens out there is that people might use tools of Riemannian geometry, like the exponential map, logarithmic map, thinking that they can use a single tangent space as if it was the Lie algebra. But this is not possible as long as you actually consider in the first place that it's a Lie group. And this is a misconception that we see every time because people think that the Lie algebra somehow is equivalent to have a single tangent space on a Riemannian manifold. And we wanted to highlight that fact. So for example, here we have two works on which we are able to learn dynamical systems on Lie groups using the tools of the Lie groups. And equivalently, we have another work where we are actually able to learn dynamical systems on Riemannian manifolds. But the tools are completely different, right? So the analysis and all the guarantees that we can provide built on completely different theories. The fifth fallacy is mainly like a kind of experimental based fallacy. So if we have a look at the data that we have here in the plot, we have an S-shape, a very tiny S-shape and a very big S-shaped trajectory. If I use the log map to project that to a single tangent space, for the one that is very tiny, you see that the distortion is actually very small. So sometimes what we have observed out there with some works is that in people running some toy examples, they actually use data that are concentrated in a very small region of the manifold. And therefore, when they compute some statistics or some optimization, the fact that the data that they use is tightly grouped in a small region of the manifold creates this fallacy, this misleading analysis of the results that a single tangent space might suffice the purposes. However, this is not true, of course, because if our data actually now spans a big region of the manifold, therefore now the projection of the tangent space shows high distortions, and therefore any kind of algorithm that we run on the tangent space won't work anymore. There are other fallacies out there, but I think these ones are the most common that we found in some published papers. And what I want to do now is basically to wrap up with some few advices that we believe are relevant besides all that we have discussed in the different talks that I think the messages are actually very clear. I think the first one is that we can think of how to choose a proper tangent space. And this is actually a question that we are asked all the time. Like, okay, can I just find a proper way to define a tangent space for my problem? And the first thing is that we actually need to think of choosing a sufficient number of tangent spaces to actually represent your data if you're running like a learning algorithm. So this is exactly what happened, for example, in the case of the Riemann and Gaussian distribution. Another way to see this is that we should choose, we call it informative base points for each tangent spaces. So basically, you want to choose, in this case, 3 tangent spaces corresponding to the clusters that we have for the Gaussian mission model. We could definitely use different kind of base points for these tangent spaces, right? In this case, we choose as the base point the Freshet mean, because I think locally is still a good way to compute the base point for the tangent space. However, there might be other ways in which we could actually learn the base point of the tangent space so that we can somehow vary this as a function of any kind of input and exploit the full tangent bundle according to where we need to have this tangent space to operate later on with the specific algorithm that we need to implement. Then there is actually relates a lot with the fact of solving Riemannian ODEs, for example, for first order dynamical systems. So here, what happens is that some of the approaches need to roll out an ODE on a Riemannian manifold, and there are different ways to do this. So some approaches are called projection-based approaches, where they just kind of disregard that they are on a manifold. They roll out an ODE for a certain number of iterations, and then they project back with a projection operator. However, this is not this is a quite inaccurate way to solve an ODE in a Riemann manifold. Another way to think about the problem is using the notion of dynamic charts. So you remember at the beginning of the talk, Noemi talked about charts and the atlas notion, and how we can exploit this notion of charts to actually define a chart using our log map, for example. This is a way to define a chart locally, and roll out an ODE for a certain number of iterations, and then use the exponential map to go back to the manifold. How many charts we choose and how many iterations we take to solve the ODE on the tangent space on the chart is still a design choice that we have to consider. This might be easier in constant curvature manifolds because we know that the change of the curvature actually is constant, obviously, but in non-constant curvature manifolds, this choice can be probably harder to make. Then, is there any application or problem where a single tangent space might suffice? And this connects with some of the fallacies that we actually didn't cover here, and is the fact that when we formulate the geodesic regression, a geodesic, as Noemi explained in the morning, basically is defined by a point on the manifold and a velocity, which this velocity lives on the tangent space. This doesn't necessarily mean that we are solving a geodesic, like a linear regression on the tangent space. What this means is that the geodesic is actually intrinsically defined on the manifold, but of course, it depends on the direction of the velocity under which we can actually throw the geodesic along the manifold. So what happens in geodesic regression is that we still need to measure the errors of the regression problem on the manifold using geodesic distances, and the geodesic basically corresponds to the exponential map of our point U, that is defining the velocity of our geodesic on the tangent space with respect to the point P, that is the base point of that tangent space. But this doesn't mean that we are solving a problem on a single tangent space. There is recent work where some authors have tried to come up with something that we call kind of curvature-corrected tangent space approximations, where the idea is to say like, okay, maybe it's too complicated, so let's try to assume that the geodesic distance can be approximated by a distance on the tangent space, so a Euclidean distance, times a curvature-aware correction. So this actually is computed based on the Jacobi fields for the manifold at hand. I won't go into details here, of course, but it's important to mention that this accounts for the distortion, again, for very local kind of tightly grouped data that we might have. So if your data actually is very spread on the manifold, then this correction actually won't work anymore. So it's a better approximation than just using the Euclidean distance, because it accounts for the distortion, but only very locally. So that's kind of the key message here. All right, so as a summary, I think that robot learning approaches, and in general also optimization, can be like very inaccurate when it comes to use them only on single tangent space approximations. Therefore, the suggestions is always try to design algorithms on Riemann manifolds that make them actually coordinate invariant. So that's something that comes for free when you consider properly Riemann and geometry tools. As I said before, we should actually leverage the bundle of tangent spaces to be able to travel along the manifold and to do the computations that we need to do locally on a tangent space, but that shouldn't be a single tangent space on the manifold. We should actually leverage the fact that we can move all around and use all the tangent bundle to be able to compute any kind of statistics or optimization algorithms and whatnot. And third, importantly, for example, when it comes to dynamical systems, first order, second order, it's important to still keep in mind that if we are talking about the dynamics where the state of the system lives on a Riemann manifold, such kind of approximations of a single tangent space are actually physically meaningless, and therefore we should definitely have formulations that account for that geometry and that build on a well-developed theory on Riemann manifolds and dynamical systems. So with that, I would like to close and thank you for your assistance, and I will be open for questions that you may have.
Thank you very much for your talk. I think that all the problem comes from a conceptual problem. The problem is that you're trying with the local concept, which is the tangent space, you're trying to solve a global concept, which is the topology of the manifold you're working on. You just can't do that. But there is a way of doing that, and it's precisely what I said before. If you use the Ramco homology, basically you study the topology of the thing, okay? You define forms of that, and you can define a top form on that defines your probability distribution of your manifolds. And that's the kind of tool you need to use in order to do this. Then you have a global approach, and then you can solve that. Because otherwise, you're basically using something local, and you very nicely show where it goes wrong, because you're trying to solve a global problem with a local approach.
Yeah, definitely agree. Thank you, Stefano. I think you can turn, you should switch it on, I think. Just, yeah.
Yep. This was great. Thank you so much. Do you suggest any Python packages or tools where given a Riemannian ODE, I can, like there's Riemann ODE solver basically. Are there any tools or Python packages for that?
So that's a good point. So I think in Python, these are not widely available. Okay. So there are a couple of authors and labs where they have developed their own kind of ODE solvers on Riemann manifolds. I can point you to that later offline. I don't have them in the top of my mind, okay, but they are not widely, like they are not covered in none of the libraries that we presented at the beginning in the morning.
Okay.
So, yeah.
Okay. Just as a follow-up, for such an ODE solver, should we also give information about the metric of the manifold, or do you need some additional information on top of that?
I think I didn't get the question.
let's say I have a differential equation dx by dt equal to f of x comma t, and I know that the x states belong to some manifold.
Okay.
And let's say I know the metric of the manifold as well.
Yes.
Let's say m of x. Is that all you need to solve?
That's all you need.
That's
Yes.
all you need. Okay.
That's all you need.
Okay.
Yeah.
Thank you.